In this video, we will discuss what are small oscillations, a role of small oscillation in various fields of physics, and how small oscillations helps in solving the equations of motion of a two-coupled oscillator. Generally, there are many systems in physics which are highly complex in nature, and finding a solution to them is a Himalayan task. So, there are several system or several mechanical problems which involve continuous systems, and we need to treat them as a limiting case of a system with a mutually interacting particles. So here comes the theory of small oscillation, which helps us in solving these cases. So this small oscillation helps by formulating a system of 1 degrees of freedom to the system of several degrees of freedom near the position of equilibrium. And we can use this small oscillations in the areas of physics like molecular spectra, acoustics, vibration of atoms in solids, coupled mechanical oscillators, and in solving the cases of electrical circuits. See, when you go from a single oscillator to a problem of a two coupled oscillator, the result we obtain will reveal some interesting and surprisingly new features. So, for example, if you go from a single oscillator to a two coupled oscillator, the solution in general is more complicated, or the oscillator, that means in a two coupled oscillator you will have two oscillators, and none of the oscillator in general will execute with a simple harmonic motion. But as a limiting case, for a small uh, amplitudes, the oscillator may be generalized, or their motion can be generalized as a superposition of two independent simple harmonic motion, both executing simple harmonic motion simultaneously. And these two simple harmonic motions, we call them as normal modes, and the same can be extended to a n coupled oscillator which has an n degrees of freedom, and it will have n independent modes of vibration, and their motion can be generally expressed as the superposition of n normal modes, and each mode will have its own frequency, and we call that frequency as a normal frequency and that wavelength as a normal wavelength. Now let us apply the theory of small oscillation to a two coupled oscillator. Generally we have an idea for a single oscillator. When we say a coupled oscillator, we have a two independent oscillators and which are coupled to each other. We call them as a two coupled oscillator. So to make a system as a two coupled oscillator, we take two identical masses of M, and these two masses are connected to a neighboring walls or a fixed walls by two massless springs which has a force constant K. And these two masses are also coupled to each other by a massless spring of force constant K prime. So when the system is in equilibrium, the springs do not exert any force on each other, but even though if the springs exert force on equilibrium, the vibration will not be affected by any means. But when you displace the system from its equilibrium position, the motion of the two masses also gets disturbed, and it is also restricted along only the line joining the two masses. That is, they can vibrate or they can oscillate only along the longitudinal mode. So for example, the masses are tied up along the x-axis, then their degrees of freedom can be well represented by the generalized coordinates x1 and x2. So this is how the system will look like. So this S1 and S2 is nothing but that is the wall which are fixed or the position which are fixed constantly, and we have a mass m from S1 which is tied through a massless spring k of force constant k, and similarly another identical mass m is also tied from S2 through a massless spring of force constant k. So, and their position or the origin is marked as O1 and O2. Then these two, S1 to M1 will represent one oscillator, and S2 to M, they will make another oscillator, another linear oscillator. We can call exactly as an two linear oscillator. These two linear oscillators are coupled together by another massless spring which has a force constant k prime. So, the picture A represents the two coupled oscillator at an equilibrium position. So, next what we are doing is, after some time t, we are trying to displace the first mass through a certain distance. So, if since they are coupled, the disturbance in the first oscillator will influence the displacement in the second oscillator. So, if I move the first mass through a distance x1, and the spring there gets elongated, and the mass m is, the second mass m is also displaced through a same distance x2, and the spring near the mass m gets compressed. So, the displacement in one case, the spring gets elongated, and in the other case the spring gets compressed, but the displacement is the same in both the cases. That means the x1 and x2 will be the same. So, we know the generalized coordinate chosen here is x1 and x2. So, we say q1 is equal to x1 and q2 is equal to x2. So, this is a written error here. So, q1 is equal to x1 and q2 is equal to x2. So, these are the two generalized coordinates which will represent the two oscillators. So, this system is an example for a two coupled oscillator. If these two coupled oscillators are not connected, that means this m and m is not connected by the massless spring which has a spring constant of k prime, then each oscillator will vibrate with a frequency with its own natural frequency omega naught, which is given by root of k by m. If these two masses are connected by a spring of force constant k prime, the system then oscillates with a different frequency other than their natural frequency. So, generally to solve to get an equation of motion, what we do, first we find what is the kinetic energy of the system, then we find the potential energy of the system, then we will find what is the Lagrangian, L is equal to T minus B, then we will solve this Lagrangian using the Lagrangian's equation of motion. The same procedure we are going to follow here. First we will find the kinetic energy of this oscillating system, which is represented by T. In general, the kinetic energy is equal to half mv square. So, v is nothing but the velocity. Here the velocity is x1 dot. Since we have a two oscillators here, the kinetic energy of the system is given by T is equal to half mx dot square plus half mx2 dot square. Then potential energy of the system is given by V is equal to half k x1 square. This k is nothing but that is the spring constant or the force constant. For the case of a linear oscillator, the potential energy is equal to half k x1 square, which we would have solved in our UG level itself. So, V is equal to half k x1 square for the first oscillator. For the second oscillator, it is half k x2 square, and now comes the term due to the interaction between the two identical mass. So, it is half k prime x1 minus x2 the whole square. So, this third additional term will create more and more problem when we try to solve this the case of the two coupled oscillator. Next, quickly write the Lagrangian of the system, which is given by L is equal to t minus v. Substituting the values of t and v here, we get half mx1 dot square plus half mx2 dot square minus half k x1 square minus half k x2 square minus half k prime x1 minus x2 the whole square. Then the Lagrange's equation of motion, generally we know d by dt dou L by dou qj dot minus dou L by dou qj equal to 0 for a conservative system. Here we have two coordinates, two generalized coordinates, one in terms of x1 and another in x2. So we write two equations of motion, two Lagrange's equation of motions, one in terms of x1, other one in terms of x2. So the equation goes like this: d by dt dou L by dou x1 dot minus dou L by dou x1 equal to 0. The second equation is d by dt dou L by dou x2 dot minus dou L by x2 is equal to 0. So we have the Lagrangian function L. Let us substitute in equation 2 and 3. Then solving, we will obtain the equation of motion as mx1 double dot plus kx1 plus k prime x1 minus x2 is equal to 0, and mx2 double dot plus kx2 minus k prime x1 minus x2 is equal to 0. So we see this the third term. In both the equations 4 and 5, the third term is the result of coupling between the two oscillators. So we can very easily get a solution for x1 if we know the value of x2. In the same, similarly, we can get the value for equation 5 if we know the value of x1. So in fact, these are the coupled differential equations which needs to be solved simultaneously, and we have a ready-made solution for these kind of differential equations, which we can write it as x1 is equal to a1 cos omega 1t plus phi 1 plus a2 cos omega 2t plus phi 2, and x2 can be written as a1 cos omega 1t plus phi 1 minus a2 cos omega 2t plus phi 2. Here this a1, a2, phi 1, phi 2 are some arbitrary constants which we have used for our simplicity. So now equation 6 and 7, we can verily understand we have each coordinate as the superposition of two simple harmonic motions of two different frequencies. That means in x1 and x2, each coordinate will involve two frequencies omega 1 and omega 2, and this omega 1 is nothing but that is the natural frequency with which each linear oscillator would have oscillated, which is given by root of k by m, and omega 2 is nothing but it is root of omega naught square plus 2 omega c square, that is the critical frequency which is given by omega c is equal to root of k prime by m. So let's quickly discuss about the normal coordinates and the normal modes in which the two coupled oscillator will oscillate. So first what I am doing is I am taking a2 is equal to 0. So and let us substitute in equation 6 and 7. So the second factor will completely vanish. So x1 will be equal to a1 cos omega 1t plus phi 1, x2 will be equal to a1 cos omega 1t plus phi 1. So this is one possibility. Another possibility is put a1 is equal to 0, and we can find x1 will be equal to a2 cos omega 2t plus phi 2, and x2 is equal to minus a2 cos omega 2t plus phi 2. See, in both equation 8 and 9, we can see in first case the oscillator or the coordinates are the same. The expression for the coordinates x1 and x2 are the same. That means if a2 is equal to 0, the two masses oscillate together in phase with the same frequency or with a single frequency omega 1. So the mass m1 will also oscillate with a frequency a1 cos omega 1t plus phi 1, and the second mass, identical mass, also will oscillate with the same single frequency a1 cos omega 1t plus phi 1. So this is the case if A2 is equal to 0. What if A1 is equal to 0? It is simple. These two masses will oscillate with the same frequency omega 2 but not in phase with each other. So they will be out of phase by pi radians. So we have a two modes of oscillation, each involving a single frequency, which is called as the normal modes of vibration of the system. And thus for the given normal mode, all the coordinates x1 and x2 will oscillate with the same frequency. Let's add equation 4 and 5 and see what is the result here. So when you add equation 4 and 5, you will get m into d square by dt square, x1 plus x2 plus k into x1 plus x2 is equal to 0. So let us bring divided by m. When you divide it, you will get d square by dt square, k x1 plus x2 plus k by m. This k by m is replaced by omega naught square into x1 plus x2. In the same way, you subtract equation 5 from 4. When you subtract it, you will get m into d square by dt square x1 minus x2 plus k plus 2k prime into x1 minus x2 equal to 0. Again divided by m, you will get d square by dt square x1 minus x2 plus k by m plus 2k prime by m. So which we have replaced it by omega naught square plus 2 omega c square into x1 minus x2. Now let us introduce two new coordinates, capital X1, which is x1 plus x2 divided by 2, and capital X2 is equal to x1 minus x2 by 2. So let us put this capital X1 and x2 in equation 10 and 11. So look at equation 10. So it becomes d square by dt square into x1 plus omega 1 square into x1 is equal to 0. And this equation 11 becomes d square x2 by dt square plus omega 2 square by x2 is equal to 0. So now the motion of the coupled system is now described by two uncoupled differential equations. So we have initially we had an equation which involved both x1 and x2. Now we have brought down it to an uncoupled differential equations, each involving x1 separately and x2 separately, and each differential equation when you solve you will get a solution which represents a simple harmonic motion of single frequency, either omega 1 or omega 2. And the solution for this equation 12 can be easily written as x1 is equal to a1 cos omega 1 t plus phi 1 and x2 is equal to a2 cos omega 2 t plus phi 2. So these solutions are obtained after decoupling the coupled equations, and each mode we call it as an normal mode, and each mode has its own normal frequency called normal frequency omega 1 and omega 2, and the coordinates x1 and x2 are called as normal coordinates. And this amplitude and the phase constant for the first mode, which is represented by x1 is equal to a1 cos omega 1 t plus phi 1, and for the mode 2, a2 and phi 2 are the amplitude and the phase constant for the second mode. So the general motion of the oscillating system is expressed by the coordinates x1 and x2. So x1 is nothing but it is the combination of capital X1 plus capital X2, and x2 is equal to capital X1 minus x2. So that our small x1 becomes a1 cos omega 1 t plus phi 1 plus a2 cos omega 2 t phi 2, and x2 is equal to a1 cos omega 1 t plus phi 1 minus a2 cos omega 2 t plus phi 2. So this equation is identical with the equation number 6 and 7 which we obtained initially. Thus we say the displacement of any mass is simply a linear combination or the superposition of the two generalized coordinates or two modes x1 and s2 which oscillates simultaneously. And And again, it is to be noted here, if the system is oscillating in one mode or other, that means if A may be equal to 0 or A2 equal to 0, both the masses execute simple harmonic motion. So in all other states of vibration, the displacement of each masses x1 or x2 depends on both mode frequencies on omega 1 and omega 2, and the oscillator will no longer a simple harmonic one. So let us discuss what are the two modes. We can say the two modes are symmetric and anti-symmetric mode. So the first mode, so in one mode, if you say x2 is equal to 0, the x1 is responsible for the motion of the coupled oscillator. So in this case, x2 is equal to x1 minus x2 by 2 is equal to 0. So which will give x1 is equal to x2. And we have the value for x1 as a1 cos omega 1t plus phi 1, which is here x1 is also equal to x2, which means that in symmetric mode, both the masses, by looking at the diagram, we can see both the masses get equally displaced and they are in phase, which means either they go along the left direction or they get displaced along the right direction through a same distance, and they oscillate with the same frequency omega 1, which is root of k by m, and they keep in phase with each other. This mode is called as a symmetric mode. Then antisymmetric mode or the mode 2, for this case x1 is 0 and the complete motion is described by the normal coordinate x2. So x1 is equal to x1 plus x2 by 2 is equal to 0, which gives us x1 is equal to minus x2. So we know the value for x2 is equal to a2 cos omega 2t plus phi 2. That means so x1 is equal to minus x2 will physically say the coupled oscillators are out of phase with each other by pi radians or by 180 degrees. So from the pictorial representation, we can easily see either the masses, both the masses get displaced through a same distance, either they approach each other or they go far away from each other. They vibrate towards each other or away from each other. So this mode is called as an antisymmetric mode. Here both the masses have equal and opposite displacement and they oscillate with the same frequency omega 2, which is given by root of k plus 2 k prime by m, and this mode is called as an antisymmetric mode. So generally it is observed in a symmetric mode, these two oscillators vibrate as if there is no coupling between them, and their frequency is same as that of the frequency of a single linear oscillator, or with them oscillate with the natural frequency. In the antisymmetric mode, the coupling is also still the coupling is working, but the vibration is out of phase by 180 degree, and the frequency is also seems to be higher than the frequency of a spring mass system, that is the linear harmonic oscillator. In general, we can say the motion of the two coupled oscillators will be a superposition of